Hello everyone and welcome to video number 5 in the Transformers course. If you follow this topic, in the previous video, video number 4, we covered the exact equivalent circuit and we found it somehow is complicated in the analysis. So in this video, we are going to cover the referred exact equivalent circuit to simplify the analysis of the transformer. Let's start. As a quick reminder from video number 4, this is the exact equivalent circuit not referred to any side. So this means that we have a primary side and secondary side. In the primary side, we apply a supply voltage V1 and we have the primary impedance R1 plus GX1 and we have the magnetizing branch R core and XM. R core representing the core loss and XM representing the magnetizing reactance. We have the ideal transformer in between where the turns ratio is N1 to N2, and then we have the secondary side R2 plus JX2. That one is a secondary winding impedance and that one is connected to the load and the load voltage is V2. Also, let me remind you about the impedance transfer or referring. So what the value of the impedance seen from the primary side or vice versa, it depends. So if we have a primary voltage V1 and we have a secondary voltage V2, so what will be the value of Z load in the primary side? We call it Z load dash, and that one depends on the turns ratio where V1 over V2 equals N1 over N2 equals A, and for the currents I1 over I2 equals N2 over N1 equals 1 over A. And we proved in video number 3 that Z load dash equals A square Z load, and that one will be applied to any impedance going from the secondary to primary, and if it's going from primary to secondary will be 1 over A square. This is the exact equivalent circuit not referred to any side. What is the problem for this circuit? We have in the middle ideal transformer, which complicates the problem. So we need to remove this one. If we remove this one, that time we can move R2, X2 and Z load to the primary side. And they will be Z load dash, R2 dash and X2 dash. And then we can connect the circuit to be one circuit like what we do now. So that one will be one circuit where we have the primary side V1 R1 plus GX1 and the secondary side now referred to the primary will be R2 dash plus GX2 dash and Z load dash, and the voltage of the secondary will be transferred to the primary will be V2 dash. So in this case we have some equations where Z load dash equals A square Z load, R2 dash will be A square R2, X2 dash will be A square X2, and V2 dash according to the equation V1 over V2 equals N1 over N2 equals A. So V1 here somehow equals V2 dash. So V2 dash equals AV2 and I2 dash equals 1 over A I2. Let us take an example. Step down transformer 400/200 volt has the following parameters not referred to any side. We have R1 equals 1 ohm, R2 equals 0.25 ohm, X1 equals J1.5 ohm, X2 equals J0.4 ohm, R core equals 1 kilo ohm, and XM equals J350 ohm. The transformer is feeding a load, Z load equals 5 angle 30 degrees ohm. We need to find the transformer impedance referred to the primary side. So firstly we need to start by the turns ratio. A equals 400 over 200 equals 2. And in this case, R1 and X1 will be the same. R core and XM will be the same. But we are going to transfer R2, X2 and Z load. So that one is the exact equivalent circuit not referred to any side. So Z load dash equals A square Z load. We have A equals 2, 2 square equals 4, 4 multiplied by 5 angle 30. So Z load dash equals 20 angle 30 degrees ohm. And if we have that one in the rectangular form, that one will be 17.32 plus J10. And R2 dash equals A square R2, 4 multiplied by 0.25, 4 means 2 square equals 1 ohm. And X2 dash equals A square X2, 4 multiplied by 0.4 equals 1.6 ohm. So the equivalent circuit will be as shown in the figure. We have the primary side still the same R1, X1, R core and XM, but the secondary is referred to the primary R2 dash, X2 dash and Z load dash. So the angle of Z load dash is not going to change with the referring, so we have angle 30 degrees. So now we can solve this circuit using circuit analysis theorems. What will be the case if we like to transfer or refer the impedance to the secondary side, not the primary side? So we are going to move R1, X1, R core, XM, and V1 as well. So we are going to remove the ideal transformer. Then we are going to move this part to the secondary equivalent circuit. So in this case, we have the new equivalent circuit here. V1 dash, I1 dash, R1 dash, X1 dash, R core dash, XM dash. So R1 dash equals 1 over A square R1. V1. X1 dash equals 1 over A square X1. R core dash equals 1 over A square R core. And XM dash will be 1 over A square XM. And V1 dash will be 1 over A V1, while I1 dash equals A I1. So this circuit, if we are going to transfer to the secondary side, again we can solve it using circuit analysis theorems. Let's take an example, and we are going to repeat the previous example, but this time we are going to transfer the primary side to the secondary side. So the turns ratio is still 400 over 200 equals 2. So in this case, R1 dash equals 1 over A square R1 equals 1 over 4. 4 means 2 square, so that one will be 0.25 ohm. X1 dash equals 1 over A square X1 equals 1 over 4 multiplied by 1.5 equals 0.375 ohm. R core dash equals 1 over A square R core equals 250 ohm, and in this case XM dash equals 87.5 ohm. So what will be the equivalent circuit in this case? So the equivalent circuit will be as shown in the figure. We transferred all the primary values to the secondary side, and now we have V1 dash and I1 dash as well. So the load is still the same, R2 and X2 will be the same, but we transferred the primary to the secondary, and we can solve this circuit using circuit analysis theorems. Let us take a comprehensive example for this part, which is referring to the primary or secondary for exact equivalent circuit. We have a 10 kilovolt ampere 2000/200 volt 50 hertz step down transformer, has the following parameters not referred to any side. So primary winding resistance of 4 ohm, primary leakage reactance of 8 ohm, secondary winding resistance of 0.04 ohm, and secondary winding reactance of 0.08 ohm. The equivalent core resistance is 20 kilo ohm and the magnetizing reactance is 5 kilo ohm. The transformer is operating at full load with a lagging power factor of 0.8, and the secondary load voltage is set to 200 volt RMS value. We need to find the equivalent circuit referred to the primary side. So this means that we need to refer R2, X2, and if we have Z load, we are going to move it. If we don't have Z load, we are going to move V2 to be V2 dash. And we need the primary voltage in this case and the transformer power factor. The turns ratio is 2000 over 200 equals 10, and the exact equivalent circuit not referred to any side as shown in the figure. What we need to do, now we need to calculate or to find the equivalent circuit referred to the primary side. So we need to calculate R2 dash, where R2 dash equals A square R2. A square means 10 square, 100 multiplied by 0.04 equals 4 ohm, and X2 dash equals A square X2 equals J8, and V2 dash, we are going to transfer V2 to the primary side, will be V2 dash equals AV2 will be 10 multiplied by 200 equals 2000 angle 0. We're not going to change the angle. So we are going to assume as well that the secondary voltage has angle 0. That one will be the reference value. So when will be transferred to the primary side will be V2 dash equals 2000 angle 0 degree volt. This will be the exact equivalent circuit referred to the primary side. We have R2 dash, X2 dash, and V2 dash. Part B, we need to calculate the primary voltage. To calculate the primary voltage, we need to know the currents everywhere, but we know that V2 dash equals 2000 angle 0 degree volt. What's I2 dash? So first we need to calculate I2 dash. Given in the problem that the transformer is operating at full load, so what is the secondary current at full load? So I2 equals S over V2, 10,000 over 200 equals 50 ampere. So what's I2 dash? So the secondary current referred to the primary side, I2 dash equals 1 over AI2 equals 1 over 10 multiplied by 50 equals 5 ampere. But what is the angle of I2 dash? The load power factor is 0.8 lagging. That one is given. So cosine theta V minus theta I for the load equals cosine 0 degree minus theta I equals 0.8. So theta I equals minus cosine inverse 0.8 equals minus 36.8 degrees. So I2 dash in this case equals 5 angle minus 36.8 degrees, which is in rectangular form will be 4 minus J3 as shown here. We know now I2 dash, but it appears here that we have a new voltage at this point. It's called V star. If we know V star, we are going to calculate I core, we are going to calculate IM, then we can calculate I node. If we know I node plus I2 dash will give us I1, and then we can calculate V1. We are going to solve the problem step by step. So let us calculate V star. How we are going to calculate V star? We are going to use Kirchhoff voltage law in this loop, where V star equals V2 dash plus I2 dash Z2 dash. What is Z2 dash? So Z2 dash equals 4 plus J8, or in a pull-up form 8.94 angle 63.43 ohms. So V2 dash, after using these calculations, will be 2000 angle 0 plus 5 angle minus 36.8 multiplied by 8.94 angle 63.43. So the voltage at this point will be 2040.1 angle 0.56 degrees volt. Now we know the voltage between these 2 points, so we can calculate I core and IM. So I core equals V star over RC. So I core equals 0.102 angle 0.56 degrees ampere, and we can have it in the rectangular form as well. IM equals V star over JXM. So please don't forget this 90 degrees. So in this case, IM equals 0.408 angle minus 89.44 degrees ampere. So in this case, we can add I core and IM to get I node, where I node equals IC plus IM. So I node equals 0.10499 minus J.4069, or in a polar form will be 0.4202 angle minus 75.53 degrees ampere. Still, we didn't calculate V1 yet, but we succeeded to calculate I node and I2 dash. Now we need to calculate I1. Now we can calculate the primary current, where the primary current is I node plus I2 dash. We are going to add them in rectangular form, then convert it to polar form. So I1 equals 5.335 ampere, angle minus 39.7 degrees. So the voltage V1 can be calculated using Kirchhoff voltage law in this loop. Now we know V star and we know I1, so we can calculate V1, where V1 equals V star plus I1 Z1. What is Z1? 4 plus J8 equals 8.94 angle 63.43 ohms. So the primary voltage, if we use this equation, will be 2084.1 angle 1.08 degrees volt. And if you notice, the voltage in the primary is not 2000 volt. You know that this transformer is 2000 over 200 volt. That one is the Turner's ratio for the ideal transformer. If we kept the secondary voltage 200 volt, so the referred voltage to the primary is 2000 volt, this means V1 should be more than 2000 to push current in this transformer. So that one is kept 2000 and that one will be higher by 84 volt. But if we need to keep V1 2000 volt, so definitely that one should be lower than 2000. So we are going to calculate the last part. Part C. What is the transformer power factor? The transformer power factor is cosine the angle of the supply voltage and supply current. Cosine theta V1 minus theta I1. Cosine 1.08 minus 39.7. So that one is cosine 40.78 will be 0.7572 lagging, because the current lags the voltage. From the previous examples, we can have some key observations for a good transformer design. Number 1. To achieve good transformer performance, the winding resistance and leakage reactance should be kept as low as possible. This minimizes voltage drop and reduces losses. Also, we notice the referred impedance remains close to the impedance level of the site to which the quantities are referred, allowing the equivalent circuit to accurately represent the transformer behaviors. So please refer back to examples 3, 4, and 5. The core plays a crucial role. By using a material with high permeability, a large magnetizing reactance is obtained. This makes the magnetizing branch impedance much larger than the winding resistance and leakage reactance. In addition, core resistance is significantly larger than the magnetizing reactance. Together, these core characteristics ensure that the current required to establish the magnetic flux remains relatively small. As a result, the no-load current is predominantly inductive and represents only a small fraction of the full load current. Because the no-load current is small enough, its effect on the overall current is often negligible. Consequently, the primary current is approximately equal to the secondary current referred to the primary side, or vice versa. Taken together these observations, we notice that V1 is close enough to V star, close to V2 dash. This means the voltage drop across the secondary impedance referred to the primary is comparable to the primary impedance voltage drop. From the previous observations and solved examples, we notice that the magnetizing branch introduces an additional load into the equivalent circuit, although this increases accuracy but adds some complexity to our solution. So its impact on many practical calculations is relatively small. This allows us to simplify the equivalent circuit while still preserving the key behavior of the transformer. This is what we are going to cover in the next video. What will I watch in video number 6? In video number 6 we are going to cover referred approximate equivalent circuits. See you in the next video.